Hello, everybody. Welcome to our presentation for Sled. This will be our final presentation for the project. My name is Yasmin Youssef. Also presenting is Colby, Lars, June, and Thomas. So the market need that we were trying to address is that a lot of the snowmobiles on the current market are not accessible for people who are differently able. And if they are accessible, there needs to be a lot of expensive modifications that need to be done to each snowmobile to make it accessible for that person. Furthermore, they're really expensive to own independently as a person. They're inconvenient for the person to use. Also, there's not really one in existence just for simple sliding on the surface of a lake, for example. And they're also hard to transport for the user. So we kind of have this niche market, and we're trying to address a need for people who are differently able. So the solution that we came up with is Sled. We had kind of some constraints that we wanted to go by, which was one, for it to be reasonably priced. This is a vehicle that should be able to be independently owned by someone. And so price is really a big factor here. Second, that it's easily transportable. Third, that it is lightweight. Both of these specifications are specific to the fact that someone would have to own this and move it around. And so if you're able to make it foldable or able to be put in different cars, that would be ideal. Finally, that it's easy to use as well as able to be used with ice that is 5 inches or greater in depth. We picked the 5 inches or greater depth because that's the specification often used for snowmobiles. And that's the kind of the amount of ice you need in order to be able to safely hold up the device as well as the person. Finally, we put great importance on making sure that this device is able to be independently operated by the operator or by the user rather, because it's hard to kind of push something on snow, but if someone's able to kind of press a button and that's all they would have to do to move, then that's great for the user as well as the people around the user. Also, this is excluding getting in and out of the device, so someone would have to help the user get in and out. So these are kind of the pictures that we have of the mock-up that we made. So as you can see from also the first presentation we did, we kind of have the top plate with a seat where the person can sit. We have a frame around it so that way if the device does tilt over, they're protected. Then we have trusses for both sides of the device, protecting the gears inside. We have kind of treaded wheels because those are the best to be used on ice conditions. And there'll be 2 different motors independently operating each wheel. So that way there's not too much stress put on one motor. And so you can see all the way to the left here, the final kind of put together mock-up.
In terms of the specifications, such as like the size of the product, we want it to be about a meter long, 2 meters high. That we wanted the seat to be about a meter tall and half a meter or 4/10 of a meter wide. All of those were decided keeping in mind that we wanted it to fit a normal sized person comfortably. We also decided that we wanted it to have a max speed of 4.5 meters per second. The acceleration we decided on was 1 meter per second squared. We obviously didn't want it to be able to go too fast since it is made for differently able people. And the minimum safety factor that we decided on was 1.8 because we wanted to make sure that this was extremely safe.
So the first design consideration we looked at was the different components of the frame, of which there were 4. We did different static and fatigue analyses on these components to choose which materials to make them out of. And then we were designing this for a maximum passenger weight of 250 pounds. And then we added the weight of the chair, which equaled 127 kilograms. The first component we looked at were the side trusses. So the loading on the side trusses is just the distributed load from the rider, and then we did fatigue analysis from the rider getting on and off over time. So we first drew a free body diagram, and the problem was statically indeterminate. So we decided to use ANSYS to simulate the loading and solve for the stresses and the reaction forces at each node. And then based on these stresses, we selected hollow square 1060 aluminum bars for the material for the truss. This design resulted in a safety factor well over 1.8, even during fatigue loading. The axle was the next thing that we looked at. The loading on the axle is fatigue loading as it's spinning. It has to be able to withstand the weight of the frame and the passenger, as well as the torsion created by the forward force on the wheels. So there's definitely a lot of loading happening on the axle, but the calculations were pretty simple, and we resulted in finding that AISI 1035 cold drawn steel will adequately handle all of these stresses. The next component we looked at was the roll cage, which is just a simple truss. And the way we designed this roll cage is that it only needs to be able to withstand the weight of the entire cart and rider one time. So we did buckling analysis on it, just in the event that the cart flips over and the roll cage needs to be able to withstand all of that weight. And based on that buckling analysis, we found that 1050 cold drawn steel will be strong enough for this use case. And then finally, we looked at the top and bottom plate, which again the top plate needs to be able to withstand the repeated loading of the rider getting on and off, as well as holding up the chair. And the bottom plate just needs to be able to hold the static weight of the motor and the gearbox. We did this analysis in SolidWorks to accurately account for the distributed loading. And based on this analysis, we found that 0.01 meter thick plates of 1060 aluminum will work.
The connections for this design are obviously very important. We don't want any failures to occur. So the first connections that we considered were the connections of the side truss. The side trusses are the most load-bearing components of this design. So we had to ensure that they were safe and sound. We did fatigue analysis on the most loaded member, which is the furthest member to the left in the drawing on the right. And it was determined that electrode 60 with a throat length of 20 millimeters would be sufficient enough to prevent against any fatigue failure with a safety factor of 2. In addition, we also did connection or failure analysis for the motor mount connections. These would be, we analyzed the torque that would be applied to the motor mounts. So they would go under cyclic loading, stretching and compressing. So after analysis, we determined that M12 grade 9.8 bolts would be sufficient enough to ensure that the motor mounts would not fail with a safety factor of 10, so very safe. We also looked at the axles, which would be mounted with bearings. So because the bearings would prevent any torque from being applied to the actual mount, it was just shear analysis in the event that the axle or the tracks would like drag essentially, causing a bending moment on the axle, and the axle mounts would be held together with 2 M4 grade 9.8 bolts, the full length of 25 millimeters. And finally, the connection with the seat to the top plate was also paramount. We wanted to ensure that the rider would not fall off in the event of sudden acceleration and deceleration. So they would be six M8 grade 9.8 bolts would be placed on either side of the chair, and that would be sufficient enough to hold the chair in place under loading of starting and stopping.
The powertrain considerations and specifications, we had to design it so that the maximum velocity of the vehicle was 4.5 meters per second, and that the acceleration was 1 meter per second squared. So as a result, we calculated that the maximum RPM or output of the drive train had to be 47 RPM, and the output of the torque had to be 24 Newton meters. Furthermore, we assumed that the gear efficiency was 96%. As you can see in the image on the right, we have 3 sets of pinions and gears with a 3-to-1 ratio, as we'll see later. And then lastly, we have crossed helix gears, which allow the direction of rotation to be redirected by 90 degrees, which was necessary because the width of the bottom plate wasn't wide enough to allow us to orient it all in the same direction. We needed that change of direction. So here are the parts that we chose. You can see the specifications for the motor, the pinions, the gears, and then the helix gears, which were the 2 high power metal gears. And then on the right, you can see the speed reduction and proportional torque increase. And then at the bottom, you can see that the wheel speed was 64.8 RPM finally, which was greater than the required 47 RPM. And the wheel torque was 24.3 Newton meters, which is greater than the required 24 Newton meters. Here's the calculation for the gear stress, which was done for the pinion attached to the motor. The assumptions we made were that there was medium to moderate shock, that the steel was of commercial quality, it had 90% reliability, it operated at less than 160 degrees Fahrenheit, and that it had less rigid mounting. And using all the specifications, we found it had a safety factor of 12.2 or 12.1, which is more than adequate for the job.
So after we more or less finalized our design with all those analysis that we just discussed, we carried out a cost and weight analysis on the Go Sled. In terms of weight, as mentioned earlier, the maximum weight of the rider that we are designing this for is 250 pounds. In terms of the weight of the actual Go Sled, we estimated that it was around 100 pounds. You can see that breakdown there, with the frame being 45 pounds, the treads and the wheels being 30 pounds, the motors being 20, and the cushions being 5, along with the seat, which brings the total weight to around 350 pounds. In terms of the cost, you can see the breakdown there. The total cost ended up being around $3,000 if we wanted to go ahead and construct the Go Sled. You can see some of the McMaster part numbers there. That price is a little above what we were going for, but in terms of next steps or future actions, we could definitely lower that cost by using smaller bars, reducing the thickness, because in our analyses, the safety factors were well above the minimum 1.8 in most cases. So in terms of the weight and the cost, we could reduce both. Definitely there is room for improvement there, but overall we were happy with the design.